In next few seconds, I'll give you the summary of what you will be learning today. First, we will try to understand atom. To do so, I'll take you to Abdera, Greece. The year is now 460 BC. Democritus was just born. And around 400 BC, Democritus gave us understanding of atom, and that's fascinating. And now once we have understanding of atom, then I'll take you to the Philadelphia to make you ambitious. In Philadelphia, a 46-year-old man looked through the window, he saw lightning, and he told his son William that the way God does miracle in the sky, I can do the same lightning inside our home. With the ambitions, now we are going back to France. Why we are going back to France? Charles Coulomb, inspired by Sir Isaac Newton, he discovered electric force. Newton universal law of gravity tells us F is equal to G(m1 m2) over r squared, and inspired by that universal law of gravity, he wrote the similar formula, F is equal to K q1 q2 over r squared, gives us also the ionization for energy, E is equal to K q1 q2 over r. So Charles Coulomb is a big deal. Now the year is 1785. Now I'm taking you to the Italy. Why am I taking you to the Italy? To control what? To control the behavior of electron. How will you do that? Because controlling the behavior of electron is big deal, because electrons are God. When we talk about electrons, we are talking about God. So if you can control the behavior of electron, that means you controlling the flow of electron. Since electron carries the charge, that means you harnessing the power of God. And we can do it by inventing battery, and that's exactly what we learned from Alessandro Volta, who invented the battery 1799 in Italy. Now the year is 1799. Now I'm going to taking you to Denmark. Why am I taking you to Denmark? I'm taking you to Denmark is because Hans Orsted just discovered that electric force and magnetic force somewhat connected by accident. He saw that the current carrying wire creates a magnetic field around it. Now I'm taking you back to France. Why am I taking you back to France? This time is not Coulomb. This time is Ampere. Ampere, inspired by Hans Orsted, wrote the math version of Orsted law, saying that two current carrying wire, distance d apart can attract if current flow to the same direction and repel if the current flow the different direction. That paved the way for big revolution. And that happens in England. Now I'm taking you to England. The year is 1832. Michael Faraday discovered law of induction. Law of induction tells us that electric field can create the magnetic field, can create the electric field, can create the magnetic field. He said that the moving magnet, for God's sake, moving magnet can create EMF, that can create induced voltage, that can create induced current. A big deal. Now with this power, I'm taking you to the Scotland. Why I'm taking you to the Scotland? I'm going to taking you to the Scotland because the Maxwell was born in Scotland. 1865, folks. 1865, Maxwell wrote the Faraday's invention in the form of math. The way Ampere wrote the math version of Hans Orsted equation. Now, what did Maxwell do? He, with the four differential equations, which we call Maxwell equation 1, 2, 3, and 4, he explained the law of induction, that the electric field can create magnetic field, can create electric field, which oscillate to create electromagnetic waves. He in fact calculated the speed of electromagnetic wave, and the speed of electromagnetic wave is 3 times 10 raised to 8 meter per second. The year is now 1865. The year is now 1865. Now I'm taking you to England, back to England, because so much exciting thing gonna happen in England next few years. 1897, folks, 1897, J.J. Thomson discovered electron. 1905, I'm now taking you to Switzerland. In Switzerland, Einstein just published a paper, 1905, folks. He proved atom discovered by Dalton and Democritus. He discovered the concept of atom discovered by Democritus and Dalton. Now from year 1905 to, I'm going to take you back to England. Why am I taking you back to England? Because 1912 Rutherford discovered proton. Now in England again something else happened. 1932 Chadwick discovered neutron. Help us understand what's going on inside the atom and the behavior of electron, proton and neutron, especially electron. So this is the plan for today. We talk about amount of substance, one of the fundamental quantities in the universe. The SI unit of amount of substance is mole. We'll use a case study, battery, to understand amount of substance and is SI unit mole. Let's start with atom, because electrons reside inside atom. Why electron is important? Because if you control the flow of electron, you can harness the power of God. When we are talking about harnessing power of God, we are talking about physics. We are talking about Alessandro Volta, who harnessed the power of God in 1799 by inventing battery, which allowed him to control the flow of electron. That makes up everything from car to computers to space shuttle. So how did he do that? Using copper and zinc. To understand copper and zinc, we have to look at the periodic table where all the elements from hydrogen to organoson. In 240 years, human discovered 118 elements, starting from hydrogen 1766 to organoson 2006. So to understand the periodic table, we have to understand the atom. To understand the atom, I have to take you to 460 BC to a place called Aptera. Let's make a trip to Aptera, Greece. So he was a Greek philosopher, and he philosophized that an atom is something you cannot cut anymore. So atom, smallest unit of matter. Now for about 2000 years, people believe that the atom is in fact the smallest unit of matter. Now 2000 years later, this atomic revolution moved from Aptera, Greece to Cumberland, England. Dalton, who gets credit for discovering a molecule along with Italian scientist Avogadro, published atomic theory in 1802, which gave us 5 postulates. Number 1, now if you look at this tube came from Democritus. So atom in same element, identical in mass. What are we talking about? For example, if you talk about piece of iron, this iron, for example, 1 kilogram iron made of 1 times 10 raised to 25 atoms. All the atoms, this 1 times 10 raised to 25, that has the same atomic number, and which is 26. 26. What is 26? 26 is the proton. So that's what make it iron. Now what are we talking about? Talking about that this piece of iron is made of 10 raised to 25 atoms. All right, all the atoms have same what? Same atomic number, which is 26. Now Dalton telling us that their mass is the same, which is 55.8 AMU, atomic mass unit. So all atoms in same element, which is iron, in this case 1 kilogram iron, which is made of 10 raised to 25 atoms, has the same mass, which is 55.8 AMU. Now let's say atom in different element has different mass. For example, carbon is 12 AMU. On the other hand, sodium is not 12 AMU. Sodium is about almost 23 AMU. All right. So different element. Here is one element. Here is another type of element, has different AMU. Atoms can make compound. So for example, sodium chloride, it can create a compound. All right. Two atoms can create compound. All right, and two atoms can create molecule. And with the Avogadro, he also discovered the molecules. For example, nitrogen, two nitrogen atom makes nitrogen gas, and two atom from different family, one is from metal family, one is from non-metal family, create a compound. And the same family creates the molecule, Dalton. And that revolution started in England, continues. Now, 1897, something else happened. J.J. Thomson discovered electron by cathode ray experiment. So what he did, so he shoot. So this is the power source. So he shoot the cathode ray. Before he shoot the cathode ray, he put positive over here and negative over here, positive charge over here, negative charge over here, and he shoot the cathode ray. And this is what he observed. The cathode ray behaves this way. All right, so then he conclude that the cathode ray made of atoms, and there must be some negative charge, there must be some electron inside the atom, because electrons negative charge attract the positive charge. So if cathode ray is made of atom, and there must be something negatively charged particle, which he named electron, must be inside. That means there is an electron inside the atom, and that's how he discovered what we now call electron. All right, so then it takes us to 1912, Ernest Rutherford. So Ernest Rutherford used the gold foil experiment to discover what we now call proton. So what he did, he placed a gold foil. It doesn't have to be gold foil, it could be aluminum foil. You can find it in the kitchen. In your kitchen, you can find the aluminum foil. You put the aluminum foil, and if you are Ernest Rutherford, what do? You shoot alpha particle. If you shoot alpha particle, and then you observe something. You see heat on the other side. You see flash on the other side, but once in a while you see a different behavior by alpha particle. Bounce back once in a while, that allow him to conclude that there is something inside, in the center of atom, and he call it, that must be positive. If it was not positive, then it would not bounce back. So there must be something in the middle of atom, and that must be positively charged. Otherwise, the alpha particle would not be bounced back. That allow him to understand there must be a positive charge in the center of atom, and most of the atom are hollow. How did he know that? 99% time alpha particle go through the foil and hit the other side. That allow him to understand that the atom mostly hollow. Outside the nucleus to the boundary of atom is almost empty space. All right, now 32. Now after discovery of proton, there was a problem, and the problem was this: you have consider hydrogen and consider helium, and then two positive, there is a repulsive force between two positive. Who is forcing it to be stable? Who holding it together? That's a big problem. And when there is a problem, then smart people become happy, because it gives them an opportunity to discover something. And Chadwick was very smart, and Chadwick was a smart guy, so he liked the problem, because problem give you opportunity to become famous, opportunity to discover something, and he took that opportunity and he started researching on it from 1912. And 1932, here's what he saw. Over here, and you have hydrogen over here. All right, so this is hydrogen and this is helium. So the hydrogen has how many proton? Hydrogen has one proton and helium has two. All right, so he understand that he put one more hydrogen on the top of each, on the top of the other one. So now you have proton is 1, so total proton is 2. So now they're supposed to be balanced out, but that's not what he saw. He did not see the balancing out between two atoms. Still helium is heavier. So he was thinking, what makes the helium heavy? There must be some problem. And he also understood that helium, what must hold the helium together, because inside the helium there are two positively charged particles. There must be something over here, and since they are not balancing out, even two hydrogen do not balance out, then there must be something inside the nucleus. There must be something inside the nucleus. And that's what he did. He put how many boxes? 1, 2, 3, 4. Each boxes represent one hydrogen. So that means we have 4 hydrogen. 4 hydrogen, and on the other hand you have 1 helium. 4 hydrogen and 1 helium balance out. Now I'm going to give you 1 minute to think about it and write all the information down, why 4 hydrogen balance out with 1 helium. And now pause the video and think about that. Now let's try to do it together. 1 helium gives how many proton? 2 proton. How many neutron? 2 neutrons. So 4 altogether. And 4 hydrogen gives us how many proton? 4 proton. How many neutrons? 0 neutrons. So 4. So they balance out. You get it. Now that allows him to discover what we now call neutron. Neutron is a source of a strong nuclear force who hold the nucleus together, although there is a repulsive force inside the nucleus. All right, very good. Now what did you learn last 10 minutes? This is what we learned. We learned that the story of atom began in Abdera in 460 BC, and somewhat it gave us understanding at 1932. So it took over 2000 years for human to understand the atom. Now we have a good understanding of atom because of Democritus, because of John Dalton, but mostly because of J.J. Thomson, Ernest Rutherford, and James Chadwick. It took over 2000 years for human to have a good understanding of atom. Now I'm going to take you to the periodic table. When we talk about periodic table, we must talk about Dimitri Mendeleev. When we talk about Dimitri Mendeleev, we talk about Russia, we talk about Siberia. It was 1834. Ivan and Maria gave birth to Dimitri Mendeleev. Around 1963, there were about 56 known elements. Now, Dimitri Mendeleev was so obsessed with the different type of atoms that one day he woke up in the middle of the night and he claimed that he saw so many atoms not yet discovered. And he put them down. He put them down in groups and periods. He called it periodic table. 1906, he was nominated to win the Nobel Prize in chemistry, but there was a man. There was a man named Peter Clason. Peter Clason opposed the idea to giving a Nobel Prize to a Russian. And he did not win the Nobel Prize in 1906. 1907, well, he died in February. Next half an hour and so I'll give you a full understanding of periodic table, and this half an hour will be dedicated to Dimitri Mendeleev. So let's get going. Okay, so we're going to divide the periodic table in 18 groups. And now I'm going to divide them in energy level. If you understand this 18 groups and 5 period, you would be able to understand the periodic table. So last one in hydrogen. Hydrogen is under group 1 and period 1. Helium. Group 18. Helium belongs to group 18. Okay. And lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, potassium, krypton. All right, so this is, all right, now this is the group 1. So this is group 1. Group 1 has a name, alkali. So group 1 has a name, alkali. Alkali, the group 1, what makes it group 1 is the valence electron. They do have one valence electron. Only one valence electron. For example, I'm going to show you the hydrogen and I'm going to show you sodium. So sodium valence electron, so let's draw the hydrogen. Hydrogen, you have one proton, and hydrogen one electron. So the valence electron is the electron on the outer shell. Now I'm going to do the sodium. Sodium has 11, so 11 proton. So 11 proton, and then it has, that's why I said that all of them has one valence electron on the outer shell. Okay. Group 2 has a name, alkali, kaolin, earth metal. And valence electron is 2. Electron 2. So now let me give you an example of, I don't know, beryllium. So beryllium, let's say beryllium. Beryllium has hydrogen, helium, lithium, beryllium. So the 1 and 2. So 2 valence electron, I'm going to call out them by green. So the 2 valence electrons. So valence electron are 2 for beryllium. But for group 1, for group 1, the valence electron is just 1. All right. So this has a name alkali, and this has a name alkaline. Okay. Now let's go to the group. Next group. This is called halogen. So this is called halogen. All right, so this is the halogen group. This is non-metal, and this is called novel gas. So this is called group 18. Halogen is group 17, and novel gas is group 18. What makes it novel gas? Because novel gas has 8 electron on the outer shell. 8 electron means that it satisfy the octet rule. Octet rule said that when an electron has 8 electron on the outer shell, that is a happy atom. It doesn't want to gain any more electron, or it doesn't want to lose any more electron, because it has what it wants, and that is 8 electrons. So all the novel gas from helium to neon to argon to krypton, everyone has the same 8 valence electron. That's why they are happy. That's why they are novel gas. We're going to talk more about novel gas in a second. Now I'm going to create a staircase. So this is the staircase I'm going to create. So this we're going to call it metalloid, meaning these are the semiconductor. All right, so everything to the left of the staircase. So everything to the left of the staircase, this thing are metals. So these all are metals, and this is non-metal. This to the right side of the staircase, non-metal, and the staircase, they are the semiconductor or metalloid. So these are the metals, these are the non-metals, and they are the metalloids or semiconductor. All right. So the most famous metals or most famous conductor in physics is copper and zinc. Where an electron can move freely, electron cannot move freely. An electron can move, but not very freely. Okay. Now we're going to have next thing we're going to try to understand the atomic number, the atomic mass, and atomic weight. So atomic number, let's take a boron for example. So boron, so the boron is the 510 boron. Boron has 2 isotopes, so we're going to talk about isotope as well, 5 and 11. So first we're going to talk about atomic number. So I told you in the beginning, atomic number is very important. If you remove one photon, so atomic numbers are photon. So let's if you remove one photon from boron, it's not going to be boron, it's going to become beryllium. Is going to become beryllium. If you add one more proton to boron, then it's going to become carbon. So if you remove or add atomic number or proton, then it loses the identity. So atomic number is more important than any other properties. Atomic number is the number of protons. So atomic number is 5. So both type of we have a boron 10, we have a boron 11, but their atomic number are the same. What makes boron is the atomic number. Okay, so this is boron, this is boron, both boron. What makes both boron? The atomic number. In this case, the proton is equal to neutron. In this case, proton is not equal to neutron. So this is the boron isotope. Now we're going to talk about the atomic mass. Atomic mass is number of proton plus neutron. This is called atomic mass. So what is the atomic mass for this one? All right, so proton is 5. So neutron is 5. So atomic mass is 10. In this case, proton is 5, neutron is 6. So atomic mass is 11. Now what is the atomic weight? So atomic weight, now let's find the atomic weight. 10 plus 11 divided by 2. Is this you can find atomic weight? No, you cannot find it atomic weight, because this is not how you you can find them on the earth. So this is the 20% of this. The boron 10 is like 20% of all the boron found on the earth, and this is like 80% of all the boron found on the earth. So then you should be doing it a little differently. So 20% is 0.2, 80% is 0.8. So you're going to have 0.2 times 10 plus 0.8 times 11, and that gives you 10.8 atomic weight. So this is what atomic weight. So we learned the atomic number, we learned the atomic mass, we learned the atomic weight. Now we're gonna try to understand the ionization. All right, from left to right. Something happens. From left to right, here are the things happen. Number one, electronegativity increases. I'm going to write it the dark. Electronegativity increases. Number two, this is also called energy level. Energy level 1, energy level 2, energy level 3, energy level 4, and so on. So energy level remains same. However, the size of atom become smaller. So I'm going to write it smaller. Size of atom is smaller. Now I'm going to give you an analysis. So 90-year-old lady and a heavy guy, and $1 million in the bag. 90-year-old lady carries that $1 million in the bag in the midnight, in the bronze, and the heavy guy do the same thing. $1 million in the bag, in the bronze, who would probably lose the money. All right, the robber would probably rob it from the 90-year-old lady is because it would probably take less energy to steal it from the old lady than the heavy guy. So these are the old and these are the heavy. That's what you're going to probably have to remember. All right, so this analogy you're going to keep it in mind. I'm going to help you understand what I mean when I say old and heavy. All right, so let's first understand the electronegativity. Electronegativity increases. Electronegativity is one way of understanding how badly an atom need the electron. All right, so for example, the electronegativity for hydrogen is 2.2, and electronegativity for oxygen is 3.4. All right, so the electronegativity more, that means they want the electron more. They want to protect the electron. So you need to apply lots of energy to steal the electron from them. They are like a heavy guy. All right, now second one, energy level same. What am I talking about? Energy level throughout the same. For example, let's say sodium energy level are 3. So hydrogen energy level is 1. So hydrogen, 1 energy level, 1 electron, the energy level is 1. For example, helium energy level is also 1, 2 electron. All right, so energy level are same, but atom becomes smaller. So this is the proton and this is the electron. This atom is big in size than this atom. So that's why I wrote size of atom decreases. Energy level same. It has energy level 1, it has energy level 1, but this atom is bigger than this atom. Why is that? It's because this has twice the number of proton. Twice the number of proton means twice the attraction. What do I mean by attraction? Because this is positive charge and this is negative charge. These are electron, these are proton. The proton pulls the electron and electron pulls the proton. Attractive charge, they want to come to each other. When they coming to each other, then they become smaller. They would like to hug each other. In this case, yeah, there is attraction, but a small attraction because this is twice. This is twice. So as it moves from left to right, the atom energy level are the same. However, atom size becomes smaller. Let me give you one more example so you understand. For sodium, as you know that this is the sodium, first energy level, second energy level, and third energy level, and this is chlorine. This is, I don't know, this is chlorine. All right, chlorine, you have also 1, 2, and 3 energy level. All right, okay, so 3 energy level, 17. So chlorine is 17, this one is 11. So then this one is, you have 2 and then 8, 1, 2, 3, 4, 5, 6, 7, 8, and then this one is 1. All right, and this one is 2, and then this one is 8, and 2 and 8, 10, and this one is 7. 1, 2, 3, 4, 5, 6, 7. All right, so this one has how many energy level? This one has 3 energy level, energy level 1, energy level 2, energy level 3. This one has also 3 energy level, 1, 2, and 3. However, this one is smaller than this one, is because there is 17 proton inside and there is only 11 proton inside. So 17 proton pulls the electron to the center and 11 proton pulls the energy to the center. So when 17 proton pulls the electron to the center, the atom becomes smaller. That means all right, let me make, I'm going to give you another analogy right now. So now, for example, if they go from top to bottom, so let's draw top to bottom right here. So this is top and this is bottom. Top to bottom, so the top you have is still heavy guy, this is heavy guy, and this is also still heavy guy. Both of them heavy guy, both of them have $1 million in the bag, and they walk around in the bronze in midnight. Now who would probably lose? Who would probably, if you are a robber, who you probably gonna target? You're gonna target the one that you probably need less energy to steal the money. Now this guy, the bottom guy is kind of sloppy. The bottom guy is heavy but is sloppy. He carries the bag like dangling like that. And the top guy is like he wants to protect his family. He is heavy and he carries the bag like that. Now if you are a potential robber, who are you gonna rob? The guy who carries the bag like that, or the guy carries the bag like that? You're probably gonna steal the bag, rob the man who carries the bag like that. This one are the one with the heavy guy who wants to protect the money, who wants to protect, if it is atom, wants to protect all the electron. And this guy, as you move down, is like that. Like the guy is very sloppy, dangling the bag, doesn't care whether he lose or she lose the electron. All right, so what am I talking about? I'm helping you understand that, as you know that if you move from left to right, electronegativity increases. The energy level remains same, but atom in size becomes smaller and smaller. That means it's very difficult for you, if you are a robber, it's very difficult for you to steal the money as you move this way. That means if you are atom, then another atom will have very hard time to remove the electron from you. All right, but if you are a hydrogen, it's going to be easy. If you are helium, it's going to be difficult for that reason. All right, so hydrogen being the 90-year-old lady and helium being the heavy guy. In this case, the hydrogen being the also heavy guy, but who want to protect all the electron. But in this case, the potassium probably gonna be the heavy guy, but dangling electron, like dangling the bag of money like that, so people can steal it, the potential robber. All right, so what am I talking about? I'm talking about hydrogen. We also already know that the electronegativity is what? Electronegativity is 2.2. And then potassium, for sodium electronegativity is 0.9. 0.9. And potassium electronegativity is, I don't know, 0.8, I believe, 0.8. So electronegativity decreases. So that means it's easier for you to, if you are a rover, it's easier for you to steal the money. And if you are another atom, it's very easy for you to steal the electron. And when I talk about dangling, this is what I meant. This is what I meant. So pay attention to this one. All right, now we probably gonna draw this one again, hydrogen. So the hydrogen is, all right. So the energy level increases. If as you move this way, energy level does not increases, but as you move down, energy level increases. And here's what I mean when I say energy level increases. So now sodium, for example, sodium, you have, so energy level increases. For hydrogen, you have 1 energy level. For sodium, you have 3 energy levels. Sometimes you call them shell. So energy level. Sometimes you call them shell. All right. So energy level, only 1 energy level, and energy level. Energy level, it's easy to call them shell. Energy level 3. So as you go down, energy level increases. All right, so that's one of the reasons, but the other reason I'm going to explain in a second. So as you know that this can hold left. All right, so now another thing I'm going to mention, that shield. So now the electron over here is this one shielded or blocked. All right, this one is also shielded. All right, so every energy level is shielded. So the less energy level you have, the better it is. The less energy level an atom has, the better for her to protect her valence electron. So for example, this one, the atom will have very hard time to save, to protect this electron, because there is a shield between the energy level. There is no shield between the energy level. That's one. The other one is, as I said, the dangling. All right, so if you hold your bag like that, it's easier for the rover to steal your bag. All right, so now as you see that the electronegativity as you move down decreases. As electronegativity decreases, the energy level increases. Energy level increases, electronegativity decreases. So what happened? You need less energy to ionize the atom. So this atom, you can ionize this atom easily, but you cannot ionize this atom easily. You can ionize this atom easily, but you can not ionize this atom easily. All right, this is 90-year-old lady, and this is a young man, and this is young man, and this is a still young man. This is young man but sloppy, dangling the bag like that, and this is young man who wants to protect, and of course there is no shield. Because this is energy level 1. Energy level 2 has only one shield, one block. Energy level 3, you have a block over here, you have a block over here, so they are almost nothing. Nothing. This one doesn't experience much pull toward the center, and this one cannot exert much pull to this one, is because there is a block, is shielded around the between the energy level. So you have the proton and you have the energy level. All right, so now what is going on right here? So you have energy level. This is energy. This is just energy. Energy is in electron volt. Okay. 3, atom number 4, atom number 5. You need lots of energy to remove their electron. You need almost no energy to remove their their electron, what this one be and what probably this one be. So this one would be the helium, all right. So helium, you need lots of energy to remove the electron, but lithium, you don't probably need that much energy to remove is electron. And this one is neon, you need lots of energy to remove is electron. Neon, argon, all right. So and xenon. All right, so these are all the noble gas. You can say this is hydrogen. Hydrogen, you don't need too much energy and you don't need too less energy, is probably in the middle. And why lithium is on the bottom? So let's help you understand the lithium, and then you probably understand what's going on. Hydrogen, I already told you the hydrogen. All right, so there is a loss of attraction going on. We can understand it by Coulomb's law. The energy would be K Q1 Q2 over R. This is how much energy you need to still. This is how much energy you need. So this is another energy formula. So how do you know this is energy formula? You can prove that. K is Newton meter square over Coulomb square, and Q is C, and then R is meter. All right, R is meter. Now C is C square, so C square is C square cancel, M goes to M square, only M times. So Newton times meter. Newton is kilogram, Newton is kilogram meter per second square, and there is a extra meter. So then I have kilogram meter square over second square, which is in fact energy. All right, now I proved that. So this is another equation for energy. This equation helps us understand that how much energy associated to this. Now if you do the helium, and then you will see, you will be amazed what you see. Then there is double. What is double proton. So this is helium. So then there is loss of attraction. Between these two. That's why it has loss of energy. We need helium. All right, so this is helium. But now let's talk about lithium. Why lithium is like 90-year-old lady. Okay, let's talk about that one. So lithium is 1, 2, hydrogen, helium, lithium, so it's 3. So it has 2 electrons. 1 electron and 2 electron, and then I have to draw another shell. Another shell is a disaster. So as I told you, it's shielded. There is a shield. All right. So this electron experience almost no pole due to the presence of these three proton inside the nucleus. It almost experienced nothing, is because it's shielded, it's blocked. All right, get it. Now we're going to talk about the electron configuration, and then we're going to conclude. And the orbital, we're going to talk about shell, sublevel, orbital, and electron configuration. And orbital. So what is orbital? Orbital is the spaces in which there is a high probability to find the electron. So orbital is a spaces where you have high probability to find electron, because orbital is all about electron. Each orbital can hold maximum of 2 electrons. There are 4 sublevel. One is the S, one is the P, one is the D, and one is the F. All right, so every orbital, S has 1 orbital, P has 2, so 6, 3 orbital, 5 orbital, and F has 7 orbital, 1, 2, 3, 4, 5, 6, 7. All right, so S has 1 orbital and hold up to 2 electron. it has 3 orbital, it can hold up to 6 electron. It has 5 orbitals, so it can hold up to 10 electron. It has 7, it can hold up to 14 electron. Now I'm going to explain. I'm going to help you understand the electron configuration and the difference between orbital, shell, and sublevel. All right. So electron configuration. So let's write 1s, 2s, 3s, 4s. These are the energy level. 5s. Before that, I should write N1, N2, N3. These are the energy level. N4 and N5. The s can take the maximum of 2 electron. All right, so now I'm going to write the p. 2p can take maximum of 6 electron. Now let's back to the d. D can take maximum of 10 electron. Now we can go back to F. Can take maximum of 14 electron. All right, so we are good. Now one more information I would like to give you, and that is each level how many electron can fit each level, and that we can accomplish by this formula. If I put 1 over here, get only 2 electron. Now I put 2 over here, if I put 3 over here, 18 electron, and if I put 4, 32 electron. If I put 5 over here, I get 50 electron. All right, so now let's do it for zinc, and let me give you one example by using zinc. So zinc is I believe the atomic number is 30. All right, so that means there are 30 proton inside the nucleus. All right, so now first we're going to put 2. All right, so 2, the first shell 2, and this is how you're going to do it. This is the rule, the 2. So you're going to put 2 electron, but I'm going to write it like that. Let's put 30 over here, 30 electron, 9 and 30. All right, so we 2 over there. So now we have 28 more to go. All right, so energy level 2 can feed up to 8. So we're going to go to 2s. 2s going to give us 2. All right, so that's 26 more. All right, that 26 more. All right, so 26 more. Okay, good. Now we're going to go to 2p. 2p going to give us 6. All right, so that means 20 more. 1, 2, 3, 4, 5, 6, 20 more. All right, now 3s. Now I'm forced to go 3. 3s gives us only 2. So 2. So now 18. All right. After 3s, I have 3p. 3p gives us 6. So I'm going to write 6. So then I have 12. 1, 2, 3, 4, 5, 6. I have 12 left. All right, so 3p can hold 18. I have only 8. 2 can hold 8. Yeah, 2 is done. All right, now 3 can hold up until 18. So now 4s. It looks like I have to go to 4s. Jesus. So 4s gives us 2. So I'm going to write 2. I'm going to write 2 over here so it doesn't conflict with right here. Okay. All right, so let me remind me, this is 1, this is 2, this is 3, and this is 4. These are the energy level. Hopefully I don't have to go to the energy level 5. Jesus. All right, now 4. Now 3d, I'm going to go to 3d. 3d allow me to put 10 on the 3. So if I put 10 on the 3, then it's going to give us 16, 17, 18. Wow. So I have 2 more left. So I have 2 more left. Okay, good. Now I have to go to the 4p. 4p give us 6. 4p give us 6. Now 4p, I'm going to put 6 more, but I don't have 6 more left. I have only 2 more, so I'm going to write that 2. Okay, so I'm done with this. Now let's check the shell 1 just to make sure. This is shell 1. Shell 1 has only 1 orbital. 1 orbital allow only 2 electron. Very good. Now let's see shell 2. Shell 2, I have 8 electron. Shell 3, 18 electron it allows. Shell 3, 16, 17, 18. Shell 4, 32, but we don't have 32 is because we have only 4 left. Okay, good. Now we're going to write the electron configuration. All right, so where are we going to write it? We're going to write 2p. We're going to write 3s. We're going to write 3p. We're going to write 4s, and then we're going to write, did you write 3d? No, we're going to write 3d, 1s square, good, and this is the 2. 2s square, and this is the 2. 2p6, and this is the 6. 3s square, so this is 2. And 3p6, this is 6. 4s square, and this is 4s square. All right, 4s square, and 3d10, and this is 3d10, so I don't need this. So let's count. 2, the first shell I have 2, the second shell I have 8, the third shell I have 18, and the fourth shell I have 2. So let's count. 10, 28, 30. Voila. This is the electron configuration for the zinc. There is a technical problem. The technical problem is we have to replace 3d10 by 4s square and 4s square by 3d10. To understand this, we have to understand Bohr Rutherford diagram for zinc. All right, to do the Bohr Rutherford diagram for the zinc, we have to have the chart 1s, 2s, 3s, and 4s. 4s is our last, so we want to stop here. 2p, 3p, 4p, 3d, and 4d. Okay, now let's draw the Bohr atom, the zinc atom. So I have 30 proton inside the zinc atom. I know that, so I don't have to draw that. And I have 30 electrons. So they're altogether 30 electrons. 30 electrons. 30. All right, so let's see. So 30 electrons. Okay. So now I have 2. First shell, I'm allowed to do 2. You already know that. Now let's go to the second shell. I have 28 left. I'm allowed to do 2 more on the second shell. 2 more. All right, so I'm down to 26. 2p, I'm allowed to do 6. So I'm down to 20. 3s, I have to draw another energy level. 3s, I have to expand that. 3s, I'm allowed to do 2. 3p, I'm allowed to do 6. 4s, I have to move to 4s. Okay, this is good. 4s, I'm allowed to do 2. So instead of writing, I'm going to write this valence electron because these are the valence. So I'm just going to put the electron over here and put the sign, electron sign. Just to show that these are the valence electron, delocalized electron. Alright, what is left? What is left? 3D is left. So 3D, I'm going to come over here and I'm going to put that. Okay? So now I have altogether 30. So let's count them again, just to make sure I have 30. 2. This is 2. This is 8. And this is 18. And this is 2. So 10. Yeah. So I have 30. Now let's see why I have to use that. It's because I'm gonna write this notation. Okay, so I'm going to write this one. So this one is 1s squared. Now I'm going to write this one is 2s squared. Now I'm going to write this one is 2p6. Now I'm going to write this one is 3s squared. Now I'm going to write this one as 3p6. Now I'm going to write this one as 3d10. What is left? The left is this and this, and that is 2s2. Alright, so you fix the electron configuration for zinc. Now I'm going to show you electron configuration for copper. I'm showing you electron configuration for zinc and copper is because Alessandro Volta 1799 control the flow of electron. All right, using copper and zinc. To understand copper and zinc is a big deal. So if you understand this one, you can skip the copper. If you don't understand this one, you watch the copper. Right, now I'm going to quickly show you the copper. Copper has 29 protons, so copper has 29 electrons. So I have copper. So before I do the copper, I'll write the energy level. One is all right, very nice. So we're done over there. Now we're going to get to write copper. So let's write the copper. So this is the nucleus and this is number of protons. Okay. Now 1s, 2. I'm not going to write it like that. I'm definitely not going to write it like that. Because if I write it like that, it will take, it's going to be hassle. So instead of like that, I'm going to write 2. I can write better. I can write 2 like that. 1s squared because there are 2 electrons. Now let's do the second shell. Second shell, 2s. So then there are 2. So I'm going to write 2 over here as well. 2. I'm going to write 2s squared. And now I'm going to put 2p. So as you see 2p. So 2p, I'm allowed to write 6 of them. 6. All right. Now I'm going to write 2p6. All right. So now I have to count. So I initially have 29. So 29 minus 2, 27. 27 minus 2, 25. 25 minus 6, 19. Okay, now I have total 19 electrons. So, okay, all right. So I started coming from here. So 3s, 3s can take 2 electron. So I'm going to write 2 electron over here. So now I have 17 electron left. Okay, 17 electron left. Now I'm going to go to 3p. 3p can take up until 6 electron. So 6 electron, I'm going to write 3p and I'm going to write 6. All right, so 17 minus 6 is 11. So I have 11 electrons left. So I still have a long way to go. Now let's see. 4s. Oh my God. So I have to go to the 4s. You kidding me? 4s can take 2 electrons. So I'm going to write 2 over here. So now I have the 9 electron. Now 3d can take up to 10 electron, but look what, I have a 9 electron. So I'm going to go to 3d. This is 4. So I'm going to come to 3d. I can write up to 10 electron, but I have only 9 left. So I'm going to write only 9. So 3d get 9 electron. So this is the electron configuration for copper. Now let's count them. 2 plus 2, 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. 18 plus 2 is 20. 20 plus 9 is 29. So this is the electron configuration for copper, but there is a problem over here. 7 orbital. That means S can hold 2 electron, P can hold 6 electron, D can hold 10 electron, and F can hold a 17 electron. Now let's draw the orbitals. All right, so for this one I'm going to draw 1 because S can take only 1. 2s. For this one I'm going to take right here. So this is S, I'm going to use the dark. P, I'm going to use the 2p. I'm going to write P can take 1, 2, 3. 1, 2, 3. S can take, once again, S can take only 1. This is S. This is P. P can take 3. 1, 2, 3. The S can take 1. This can take 1. And D can take 5. 1, 2, 3, 4, 5. Boss, when you have like 5 people, they sit separate. When you have 50 people, they double up. This is 9 and this is 2. Now D is strong, D is more stable. This orbital are filled. So we're going to fill this orbital. So we're going to remove this one. You're going to remove this one from S and put it on the D, because D is stable. D is stable means copper is stable. So that we're going to move it over there, and then that becomes 1 and that becomes 10. So the finally electron configuration for copper is this: 1s squared, 2s squared, 2p6, 3s squared, 3p6. When we talk about chemical bonding, we actually talk about atoms. When more than one atoms come together and join, glue together, we call it bonding. When 2 atoms from same family, for example 2 nitrogen atom, come together and join together, we call it nitrogen gas. When 2 atoms from different family, for example the sodium from metal family and the chlorine from non-metals family, come together and join, create bond, we call it a compound. So there are actually 3 types of bonding we're going to talk about today. Let's write them down. Let's write the periodic table. This is metals, this is metalloid, this is non-metal. So the ionic bonding, when a metal joins with non-metal. Covalent bonding, when non-metal joins with non-metal. Metallic bonding, when, let's see the example. Sodium, chlorine. Sodium is a metal, chlorine is non-metal. So this creates ionic bonding. Now we can also understand it by electronegativity. Sodium has electronegativity 0.93, chlorine has electronegativity 3.16. So the electronegativity between the difference of electronegativity is greater than 2. So that's why it is ionic. We can understand it different way as well, Lewis structure. So sodium has 1 valence electron and chlorine has 7 valence electron, and we can show it by sodium has 11 proton and sodium has 3 energy level. All right, the first one we know that there can be 2, and the second one there can be 8, and the third one, so altogether it has 11 electrons. For the chlorine, it has also 3 energy level, and this is 17, total 17 proton. The first one can have 2, the second one can have 8, and the third one 7. 1, 2, 3, 4, 5, 6, 7. So this electron, all right, so this one has loss of electronegativity. So this is going to steal the electron from here. All right, so this is going to steal that electron, and this electron going to end up coming over here. All right, so making this one a negatively charged and making this one positively charged. All right, okay. So we can write down the oxidation. So this is called redox reaction. So when Alessandro Volta created battery, so inside battery there is a redox reaction. So in a second I'm going to go over the battery, but this is an easy example to follow. First find the oxidation and reduction. Oxidation means, reduction means gaining electron, oxidation means loss, losing electron. This is the half reaction. When we talk about a half reaction, we talk about voltaic cell. So voltaic cell give you the half reaction. So when you join together, you have the ionic equation. So the chlorine plus and then sodium okay, so now we're gonna get the ionic equation. Ionic equation for this redox reaction, and that would be sodium plus chlorine gives us table salt. Okay, now our goal is to find the electrostatic force in this table salt. So let's give you the problem. So let's say this is Q1 and this is Q2. All right, so we want to find the electrostatic force. So let's say Q1 is separated from Q2 by distance r, and let's give a value of r. R is 3.4 times 10 raised to negative 10 meter. All right, now Q1 from the physics reference table we know 1.6 times 10 raised to negative 19 coulomb. Q2 is 1.6 times 10 raised to negative 19 coulomb. All right, so the formula we need to use is this: F is equal to K Q1 Q2 over R square, and K we know that 9 times 10 raised to 9 Newton meter square over Coulomb square. We also know the R, so we know, this is what we know, this is what we need to find. Okay, so we can definitely find it. K Q1 Q2 over R squared. All right, now let's write all the values. K is 9 times 10 raised to 9 Newton meter square over Coulomb square times, now you're going to write Q1 1.6 times 10 raised to negative 19. So sodium is positive, so you're going to write 1 charge of sodium, so you're going to write positive. And now Q2, so now let's write Q2. All right, so Q2 would be negative because this is chlorine. So negative 1.6 times 10 raised to negative 19 coulomb divided by R squared 3.14, right? 3.4 times 10 raised to negative 10 meter square. Okay, so on the left side we're going to write SI unit, in the middle we're going to write the values the whole number and decimal. On the right, we're going to write the exponent or power. So let's write them. So let's write this one first. Newton meter square over second square. Let's write, there should be coulomb over here because this is Q. So this coulomb and then this coulomb. And then the meter square because there is a square over here. Now we're going to write the values, the whole number and the decimal. So this is 9 times, this is 1.6 and this is negative 1.6. So one positive, one negative, so this there is an attractive force between them. We already see that. So 3.4 square. All right, so on the right, we're going to write the exponent or power. So 10 raised to 9, 10 raised to positive 9, negative 19, negative 19, and then negative 20, but when negative 20 goes to top, becomes positive 20. Okay, now as you see, c square and c times c is c square, m square, they cancel. So you have only Newton left. And this one gonna give you, so this is 2 times 10 raised to 29 minus 38. 2 times 10 raised to negative 9 Newton. So that much force, attractive force, you should write attractive force because one is positive, one is negative within the table solved. Covalent bonding, two types we're going to talk about. One is the polar and the other one is non-polar. Unequal share of valence electron resulted positive charge on the one side and the negative charge on the other side. Let me give you an example so that you understand what I'm talking about. Consider H2O. So let's first try to understand how many valence electron. Hydrogen has one valence electron, so 2 hydrogen, 2 times 1 plus. Oxygen has 6 valence electrons, so altogether we have 8 valence electron. So hydrogen, oxygen and hydrogen. So there are 2 hydrogen and 1 oxygen. These 2, 4 do not contribute in bonding. Now it should be look like this, but it won't be look like this because this pair of this pair of electron, they do not contribute to the bonding. All right, so now this is not good. So now it should look like then, because these 2 pair of electron who do not contribute to the bonding. All right, that creates polarization. So the oxygen has more electronegativity. In fact, oxygen is 3.14 electronegativity. The hydrogen 2.2. So that this one will be positive and this one would be negative because this has more electronegativity. This is negative, this is positive. Now talk about non-polar. So let's say the nitrogen and let's say another nitrogen. They come together and let's say the valence electron for nitrogen, I think 5. So 5 valence electron, 5. So total we have 10 valence electron. So 1, 2, 3, 4, 5, 10. But that would not be good because then this one satisfies the octet rule, but this one does not satisfy the octet rule. So what we can do, we can put this 2 over here and we can remove these 2 and put them over here. So, and we can remove these 2 and put them over here. Oh, that doesn't look good. All right, now we have 2 more, this one and this one. So this put over here, this put over here. Now let's see, both of them satisfy the octet rule. Now this one has 8 and this one has 8. Okay, so there is then triple bonding. So nitrogen, nitrogen. So 3 line, 1 line for each pair of electron. So this is nitrogen. So this create a nitrogen gas. So this is solid, the one that we show before, ionic. So this is solid, this is liquid, and this is gas. 3 form of matter. Okay, so this is the 3 form of matter. This is called diatomic, and this is compound, and this is also compound. Okay, now I'm going to show you the metallic bonding. So let's consider an iron. So iron is made of atom. This iron made of, who knows, made of millions of atoms, billions of atoms, trillions of atoms. But I'm not going to standing up here and draw all trillions of atoms this piece of iron made of, because then it will take forever. So I just draw 6 iron atoms. Each, what makes iron atom is the atomic number, which is 26. So atomic number is 26. Iron has 2 valence electron. All right, that means we're going to call them delocalized electron. Delocalized electrons are valence electron. Localized electrons are the electrons on the fast shell, or on the fast energy level. All right, so let's draw the iron, which has 26 proton inside. So the first energy level, second energy level, third energy level, and fourth energy level. The first energy level, you have 2 electrons, second energy level 8 electron, 14 electron, and then 2 electron. So these are delocalized electron. These are delocalized electron. These are localized electron. The atom always lose the delocalized electron. You get it? All right. So delocalized electron leaves the atom. When delocalized electron leaves the atom becomes positive. Okay. So these electrons create a sea of electrons. So this sea of electrons can carry charges. So when electron carry charges, they can create, when electron carry the charges, they can create electricity. Okay? When electron carry charges, they can create electricity. Okay, now what we want to know is how many atoms this piece of iron made of. So amount of substance is a fundamental quantity whose SI unit is mole. So then what is mole? Okay, so mole is like a dozen. Let's think of this way. Now, thousands of years ago, people used hand to count things. For example, the base 10 came from the fact that we have 10 fingers. Okay, base 10 came from the fact that we have 10 fingers. For example, when people used to walk and used to count things, for example, people used to see 5 cows and they had to count the cows, and they use their fingers. 1 cow, 2 cow, 3 cow, 4 cow, 5 cows. Okay, so you can use fingers to count cows. You can use dozen to count eggs. For example, you have 12 items, you have 12 things, you have 12 eggs, or you can call it dozen. So what am I talking about? I'm talking about, like, if you have 12 things, 1, 2, 3, 4, 5, 6. So you have 12 things. Or you have 12 eggs, you can say. Eggs. So you can say dozen. dozen eggs. All right, so the mole is like a dozen. So 1 mole is equal to not 12 items, not 12 items. All right, so 12 items. It doesn't have to be egg. 12 items, 12 anything items. So 1 mole is not 12 items. It's much more than that. 1 mole is, in fact, is gonna take like 10 seconds to write it. It's just too long. So if it is too long, you want to write it in scientific notation. To write it in scientific notation, you put a dot at the end. So you're going to start counting to the left. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23. So you gonna write it in scientific notation. All right, so 6.02 times 10 raised to 23 items. Now can you have 6 times 10 raised to 23 cows? No, mainly because you cannot fit that many cows on the earth. It's just going to be too many cows. Can you have 6 times 10 raised to 23 eggs? Well, no, because where are you going to fit that many eggs? You will not be able to fit that many eggs on the earth. So what is it good for? So can we use our fingers to count how many atoms in this item? No, we're going to run out of fingers. Can we use dozen to count the number of atoms in this item? No, because then it's going to be because there would be just too many iron atoms. So what can we use? Well, we can use mole. All right, let's check it out. So we have 1 kilogram. So 1 kilogram is 1000 gram. All right, so first we need the mole. All right, so 1000 gram of what? 1000 gram of iron. So we have to be specific. Times what do we need? We need it to mole and gram of iron. Now 1 mole is how many gram of iron? 55.84. Alright, so the gram and gram cancel. So what do you get? 55.84, 17.9 mole. Alright, you have 17.9 mole of iron. So now step 2, 17.9 mole of iron times, you want atoms, because that's what you want to find, how many atoms in this piece of iron. As I told you, there are more than 6. In fact, there are more than 1 million. In fact, there are more than billions. So we just don't know. So we have to calculate it. Alright, so mole. We know 1 mole is 6.02 times 10 raised to 23. Okay, so mole cancel. So we have 17.9 times 6.02 times 10 raised to 23 atom. This is about 1 times 10 raised to 25 atom. So how many atoms in this piece of iron, which is 1 kilogram? Alright, so we found it, 1 times 10 raised to 25 atoms. Alright, this 1.25 atoms, iron atoms, each and every single iron atom will release 2 electrons, create a sea of electron. This electron carries charges And when electron carry charges, what is the consequence? Electricity. One more time. This is called metallic bonding. This 1 kg ion made of 1 times 10 raised to 25 atoms. These atoms, all of them ion, cation, positively charged. What this cation can do? Well, around this cation there is a sea of electrons. Sea of electrons made by electrons that coming from the iron atoms. These electron can carry charges. When electron carry charges, it creates electricity. Voltaic cells. Alright, so what can I do? Voltaic cells. Voltaic cells is all around you. Example of voltaic cell is battery. What can you do with the battery? Well, as I told you in the beginning of this lesson, battery was invented by Alessandro Volta in 1799. That revolutionized the history of science. That's revolutionized the physics, because you can use the battery to create electricity. In fact, he did. This is, in the next 10 minutes, I'm going to show you how you can use battery to create electricity. How can you use battery to create the flow of electron to create electricity? All right, so you need 2 beakers, 1 beaker and 2 beaker. This beaker, you put some water, you add some, you make a solution by zinc sulfate and copper sulfate. All right, so you make some solution and then you dissolve alligator cliff between these two. What alligator cliff will allow? Alligator cliff will allow electrons to move from zinc to copper. All right, so now let's zoom in to see what happened. I have two things. I have the zinc metal and I have the solution. I have the copper metal, I have the solution. All right, so what happened when zinc metal dissolved in the solution? What happened when copper metal dissolved in the solution? So the electronegativity of copper is more than electronegativity of zinc. So then copper would badly want the electrons from the zinc. So because electronegativity of copper is bigger than the electronegativity of zinc. That means the copper won electron badly than zinc. Now zinc has how many valence electron? I show you a couple minutes ago that zinc has 2 valence electron. So what would happen? So I'm going to put lots of zinc over here. Let's see whether I can do that. Zinc, 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 right? So zinc would lose 2 electron. As a consequence, the zinc that lose 2 electron, because 2 valence electron, 2 delocalized electron, then zinc, this 2 zinc will become positive, cation, positively charged cation. So this zinc will be in the solution now. Okay, this zinc will be in the solution. All right, this zinc will be in the solution. Okay, so this 2 electron will go inside the copper. When they go inside the copper, it comes over here. Okay, so this solid copper becomes bigger, and this solid zinc becomes smaller. This is no longer zinc, this is a zinc ion. This is no longer copper, this is an ion. This is called anode and this is called cathode. right? So there is a two station, anode and cathode. All right, copper is started as liquid, aqueous, plus is started as a liquid, so this is 2 plus. All right, so 2 electron, that gives it copper solid. What about the zinc? The zinc is started as, this is the zinc. Zinc is started as solid. All right, so zinc plus 2, which is dissolved in the water, aqueous, plus 2E. Now we can write the net ionic equation. Alright, so net ionic equation, let's write it down. First zinc, so let's put zinc solid, okay, plus copper 2 plus liquid, turns to zinc will dissolve in the solution, so zinc solution plus copper will become solid, so copper will become solid. All right, so what did you learn? We learned that all right, let's go back to analogy. Let's say this is a lemon. You put a nail and you put a penny and you connect them by a regular clip. By connecting them, the 2 electrons from zinc will move to copper because copper has more electronegativity. So creating a potential difference between 2 stations we call anode and cathode. Anode is the positive terminal and cathode is the negative terminal. Anode is the zinc and cathode is the copper. So there is a name which is potential difference. So potential difference. Potential difference between 2 terminals, positive terminal and negative terminal, anode and cathode, zinc and copper. So what is the another name for potential difference? Voltage. After name of Alessandro Volta, who invented this in 1799. Okay, so voltage is what? Voltage is energy over charge. All right, so voltage is W over Q, and that's what we're going to prove now. How voltage is W over Q? So voltage, we know that force is kilogram meter per second square. We know that energy is kilogram square meter square over second square. Now let's see the voltage with respect to this, so you can see what's going on inside as a fundamental quantity. Alright, so kilogram meter square and second square. Now we're going to do Q. So what do we know about Q? Here's what we know about Q. I is Q over T. So we know Q is IT. So Q is AS. So now we're going to write AS over here. Now we have what? Kilogram meter square A second cube. So voltage is kilogram meter square A second cube. Now you'll get to see voltage with respect to force and energy and see their connection. I'm going to conclude this lesson by not taking you to 460 BC, by not taking you 1803 when Dalton discovered element, by not taking you 1752 when Benjamin Franklin became ambitious by not taking you 1785 when Coulomb discovered electric force, by not taking 1820 when Ørsted found the relationship between electricity and magnetism, by not taking 1823 when Ampere wrote the math version of Ørsted equation, not 1827 when Ohms in Germany wrote the Ohm's law that V is equal to I over R, the triangular relationship that explained what's going on in the circuit, not taking you back to 1832 when Faraday wrote the law of induction. In fact, yes, I'm taking you to England, 1832 when Faraday wrote the law of induction, telling us that the moving magnet can create EMF, and that can create the induced voltage. That induced voltage can create induced current. Now, the smart guy, Maxwell in Scotland, picked that idea, wrote it in the math form now we know as Maxwell equation. And Maxwell explains that when magnetic field create electric field, create magnetic field, create EM wave, which we perceive as light. We are talking about light. Now, Maxwell did not understand the light. He did not understand why the speed of EM wave is 3 times 10 raised to 8 meter per second, why it does behave the way it does. Now it takes us to Switzerland, 1905. Einstein published a paper, a special theory of relativity, paper number 4. In that paper he explained why. Paper number 3, in that paper he explained, he gave us the behavior of light. He is telling us that light is not only wave but also particle, that when electrons jump up by photoelectric effect theory, when electrons jump up, when it gains energy, and also when electrons jump down, it releases photon in the form of EM wave, which we perceive as light if it is within the spectrum of 350 to 750 nanometer. So our next topic is light, and we will try to understand the light because we want to understand the candela, and we will do it through the lens of Einstein.